I'm here to talk about Urbit. How many of you have heard of Urbit? Can I get a show of hands? Cool. That's, I think, the highest percentage I've ever encountered. That's great. How many of you know that Urbit is not a blockchain? Excellent. Still high percentage. All right, we're doing great so far. So Urbit, the talk is Urbit personal servers for the post-web. The core thesis that I'll be advancing in this talk is that the post-web needs a personal server. Why might you need a personal server? Well, let's say that you want to run a DAO. What kind of software do you need to spin up the DAO, operate it, et cetera? So some of these, you need a lot of different components. Some of these are Web3, decentralized, and some are not, right? Typically, people organize their chats on Discord, Telegram, distinctly centralized services. And even for the Web3 services, there's not necessarily a sort of unifying framework to get those all to interoperate with each other. So that on its own, that's not a full post-web, right? We're sort of halfway there with a lot of the Web3 stuff. We have blockchains, we have blockchain clients, we have a lot of other interesting technologies like that we've seen today. But as an environment, like as a user, when I sort of boot up my machine, I want to interact with the internet as a whole, we're still halfway living in Web 2. So the way out of this is by having a personal server. So what is a personal server? Well, it's a server that I run myself. So servers in general are designed to be industrial machinery, right? You might run a cloud of Kubernetes stuff running Linux and a bunch of other things, and you'd have to typically pay a lot of people to manage DevOps for that and have data centers and whatnot. The idea of running a server as an individual, it's typically considered laughable. It's like nobody wants to do that, right? I don't want to spin up an Ubuntu instance somewhere and like keep that thing running and keep it up to date and keep all the security updates. And then even if I were to install different things on that, you know, different apps and whatnot, how do I get all those to communicate? How do I have user interfaces to all of them, et cetera? So it's a big problem, right? And it's a bit subtle because for each application, it's not so bad necessarily. But when you try to put them all together, have one coherent system for sort of managing my personal digital life in a post-web manner, we're not really there yet. So Urbit is an attempt to address this. And the way we do it is we have a personal server operating system. So it's not just a sort of one application that I run on my own computer. It's an operating system into which I can install other applications, so it's extensible. And the way we do this, it's a very particular kind of personal server operating system that tries to embed this concept that we call solid state at many different levels. It's extending, so that starts at the very lowest layer of the stack and goes all the way up to the application layer. So I'm going to sort of stay on this slide for a while and describe Urbit's architecture, some of why it is the way it is. And then at the end, I'll get to the dApps, and I'll talk about some of the applications that you can run in Urbit and where we see this going, how we see this fitting into the broader post-web world. So Urbit starts with Nock. Nock is a machine code. Now, there are no processors at the moment that run this machine code, although there is a spec for one. And so there is a guy who's just starting a year-long project to actually build out a processor that runs Nock. It's a very unusual machine code. It has 12 opcodes, and if you compare that to typical x86 64, that has somewhere between 1,300 and 4,000 opcodes, depending on how you count. You need a whole book to describe it. Nock has 12 opcodes. It fits on a T-shirt, the spec. And so it has, and the way it works is instead of having a sequence of instructions that you give to the machine, which is how most machine codes work, it's an imperative. You say, do this, do that. Load this data from memory. Store this data into memory. Perform this operation, take the results, store it there. Most machine codes, almost all of them, work that way. Nock, by contrast, is a pure functional machine code. So the way Nock works, it says here is a tree of data, and the leaves are arbitrarily large numbers. They're big nums. And it says this tree, you can treat it as an expression. You run this expression, and it returns a new tree of numbers. That's it. That's the full formalism of the machine. And the whole thing's expressed in 12 opcodes. It's very succinct. And why would we want to do this? And the reason is to have this be a solid state interpreter. So that we've always called it that. Urbit is a solid state interpreter. And by analogy to hardware, right? So if you have a spinning disk, a hard drive, you have a physical disk spinning around, you have a head that moves. These things break over time. If instead you use solid state logic, meaning there are no physical moving parts, all you have is just electrons moving around, then that is much easier to keep it working for a long time. And the software analogy to this is basically being very careful with state and being very careful with determinism. So Urbit is a fully deterministic operating system all the way down to the machine code that runs everything. So the machine code runs the OS kernel. That OS kernel runs applications. Those applications engage in a networking, Urbit, peer-to-peer networking. And they're based on an identity system, and all of those are designed to be solid state. So that means that we're trying to build a very stable foundation for computing. So we start with this solid state machine code, Nock. And it's not as slow as you might think. It's not particularly fast, but we're working on that. There's actually a cross-organization team working on a project called Aries that's intending to get Nock up much closer to native speed. We'll see exactly how far that goes, but I think the ceiling is quite high. And we all do that. There's some good reasons to think that based on some of the static nature of dispatch in Nock. But then you don't want to write code in Nock just like you don't want to write code in machine code, so the next layer up in the stack is Hoon. Hoon is a programming language, and it's a systems language. So it's best thought of as a pure functional analog to C. It's really designed for hot code reloading, running other code. It can run other Nock code metacircularly at full speed. And Hoon is a very concrete language, so it's very unlike Haskell in this way, despite being a statically typed functional language. The idea is with Hoon, you know exactly what Nock is coming out of it. So I can look at some Hoon code and tell you which opcodes in Nock result from that Hoon code very easily. So it's sort of a thin layer over the machine code, for better and for worse. But it's good for writing Urbit itself, which is what it's primarily for. So Hoon is used to implement a solid-state operating system. That's called Arvo. And so what this does is this runs it runs in the virtual machine. So we have a virtual machine that's actually similar to a blockchain VM in a lot of ways, because it's also running a deterministic system. It's also similar to database VMs for the same reason. And actually, so the way this works is that Urbit is a somewhat abstract system. Like it's really a spec. And there's an implementation of the spec, but that spec is defined by Arvo, which defines the behavior of the computer. Right, so it's a virtual computer. You run it, or at least for now, it's a virtual computer. Right, you run it on Linux, you run it on Mac OS. And it can take in events, which might be a key press or a packet coming in over the network, and then it runs Nock on the previous state and the new event to get a list of effects and the new state, which is then threaded through to become the next state that takes in the next event. So that state of your computer, that includes the operating system kernel itself, like the code, the compiled code for the OS. It includes the compiled code for all of the apps that you're running. It includes all the data that's in those apps. And all of this is in one VM. So it's in one VM that's persisted to disk, like a database, using an event log. So we persist the events to disk as they're coming in. The data lives in RAM unless it needs to be paged to disk, and then periodically snapshotted, just like if you're running a database. Right? So one way of thinking about Urbit is we took the operating system, we stuffed it into a database. But one thing that this gives you is that Urbit, like databases, becomes a single level store. So from inside of Nock, I can just access data. I can just read it. There's no conception of whether that data is on disk or in RAM or stored in a distributed file system or any of that. It's available axiomatically as part of the way the system works. And this is important for local first, actually, right? Because what this means is that the system just guarantees that I have all the data I need persisted. And it's available to me as a programmer. So if I'm running an app, that app has the data. The data is in the same memory space. Right? So there's no question of like, well, which peer do I fetch the data from? All I have is the hash. Right? How do we organize the DHT? Who's storing what data? How do we incentivize the storage of the DHT? You don't have to answer any of that questions. I'm storing all the data. It's my machine. I run it. So, of course, Urbit is a general purpose system. So you can build other layers on top of it that do distribute data. You can build DHTs. You can build, and Urbit has a revision controlled file system inside of it. It's very similar. It's called Clay, very similar to Git. And so it has Git, revision control semantics, and a few other things. And it is also distributed like Git, so I can have a repository that's just on my machine. I can share it with you, right? And the network topologies of applications in Urbit vary. Each application picks it for itself. And what you typically see is these sort of multi-centric topologies. So one of the major Urbit applications is chat. And if I'm a chat host, then your Urbits will all connect to me, to my Urbit. And then I will, so each one of you could send me a request to make a new post in that chat room. And when you do, then I will distribute that data to all of you. But that's just for that chat room. So in that case, I'm the hub in a hub and spoke model. And for a different chat, maybe you're the hub, right? And so this is a sort of natural, like bottom-up evolution of the network topology that comes out of this local first mentality of saying, all right, well, what data do I care about? Okay, well, by default, I'll store that myself. So Arvo, the operating system, coming back to this slide here. Arvo, the operating system, implements a single-level store so that I actually have axiomatic access to all the data that I care about programmatically. So one of the things and I touched on this briefly, one of the things that operating system implements is a networking protocol. So, and this networking protocol, there are two of them. One is called AIMS, the other one's called Finet. There's actually a square in Paris named after Finet. He was a French mathematician and cartographer. But this network protocol is designed to be solid state. So I'll get into how that works. So, and the way it starts, the way to get solid state for networking starts with identity. Because you want to have a stable identity over time. So on the network, I'm known as Ravnus Rikfer. That's my handle. That's also my network address. So Ravnus Rikfer is a pronunciation scheme for a 4-byte number. So each byte in that number has a syllable. So there's Dalweb Donfun right there. I'm Ravnus Rikfer. And these things, they sort of sound like names in a foreign language, maybe. They're memorable. I personally remember maybe a couple of hundred Urbit IDs. And what's interesting about Urbit is that people actually do get really attached to them. This may be the best functioning part of the Urbit system. Like all this stuff works, and people run it all the time. But what's interesting is people get very attached to their names. And so it sounds like sort of a strange idea, and I think if I had encountered it abstractly, I might not think that it works, but empirically it works quite well. And so networking starts with the identity. Which node is it? Each node has a permanent identity. So when you first boot up your Urbit node, which we call a ship, when you first boot up that Urbit node, you give it that identity, and you give it an initial key pair, private and public key. And then it keeps that identity indefinitely. So the idea is I can run this for my whole life. I can pass it down to my children, and it'll keep that ID. And I get to set the keys for that ID on chain. So we use Ethereum for this. We could switch to a different blockchain if we needed to, but let's not. It would be a big pain, but we could. But what's important is we do need some sort of external blockchain to guarantee Byzantine fault-tolerant consensus on who owns which Urbit address. So at the moment, the way it works is you have an Ethereum address that owns an Urbit address, It's an ERC-721 NFT. It's like the NFT to end all NFTs, right? It's the NFT that comes with the whole operating system inside of it. So when I obtain one of these Urbit addresses, this Urbit identity, that gives me the right to set the key on chain. I can set the public key. So when I set my public key, then everyone knows how they can communicate with me, how they can send encrypted messages to me. And so this is the basis of our end-to-end encrypted peer-to-peer networking system. And then it is a structured network, unlike Radical and some of the other ones that were discussed here. So it's not unstructured. And that structure is that there are a set of, it's a federated routing system where there are 256 root nodes called galaxies, so all the 8-bit, one-syllable addresses can act as root nodes. The 2-syllable, 16-bit addresses, there's 65,000 of those are called stars, and those provide packet forwarding services primarily, or at least they will. Right now, the galaxies are doing that, but hopefully pretty soon, like this quarter, we'll turn on stars to do packet forwarding. So that's in case I'm running my Urbit on my laptop that's behind a local network, right behind a firewall, router, and we have to do NAT traversal so that other people can find my Urbit, on that local network. So you do need some relay somewhere in the public internet. So the way Urbit is structured is designed to use a little bit of economic incentivization to make it so that I can always find someone who will relay packets for me, relay packets to my ship in case my ship is behind a NAT. So there are a bunch of trade-offs there about how do you do it? Do you have no structure? Do you have some structure? We have some structure, and then the fact that there are 65,000 nodes means that I only need one of those who's willing to forward packets to me, and people can still find me. So that's going back to the Arundel talk about censorship resistance in terms of, was it filter resistance versus ban resistance? Right, so for ban resistance, it's pretty tough in Urbit because you'd have to get all 65,000 relay nodes to agree not to forward packets to me. If one of them agrees to forward packets to me, then I'm not banned. And actually, even if none of them agree, if I put my ship on a public IP, then I'm still not banned. So there's a compromise there. We actually don't do as much, sorry, that was filter resistance. Sorry, I mixed them up. So yeah, so that's for filter resistance. Ban resistance is tougher. I think if China wanted to ban the Urbit protocol, I don't think we would have very good defenses against that at the moment. I'm actually very interested in making that not the case. So if anybody has thoughts about that, let's talk about it. But in any case, we have this somewhat hierarchical routing system so that I can get a peer-to-peer connection to you that's as direct as possible, right? If you and I are both behind NATs, maybe we need a relay, but if only one of us is behind a NAT, ideally we don't need a relay, and then my ship will learn your ship's IP and port, and it'll remember that, and then we don't need anybody. It's just the two of us, and we can send network messages just to each other. What's nice about this is that there are no sort of unnecessary third parties in this, right? So it's very bottom up. If I want to communicate just with you, I can do that. No one else has to hear about it. It could be my physical computer talking directly to your physical computer. Maybe we need a relay that's end-to-end encrypted, but if we don't, we just do that. So the networking protocol, there are two actually. There's one called AIMS for sending commands to each other, requests. And there's another one that we just added a couple months ago called FINE. And this is the one that's really solid state. Because what this allows me to do is I can publish data at what we call a scry path. It's like a URL. And that path starts with my ship's address. So it starts with my identity. And I can publish an immutable binding from that path to a piece of data. So my kernel will actually guarantee that it's immutable. I'll sign the binding. We don't have Byzantine fault-tolerant consensus on the bindings. We need a blockchain for that. But you don't need it for most things. What this allows is efficient data dissemination, like a CDN, like a content delivery network. So basically, this allows my ship to effectively scale up elastically into a CDN by just publishing data immutably at these various paths. And then because the data is immutable, it can be cached forever. So it's a lot like hash address data, where you know that the hash is always valid. You also know that the scry path is always valid. So this is a way of saying, here are these pieces of data then can be used with this functional system, right? So you can run pure functions on data that's signed, you know the provenance, you know where to find it on the network, and it's referentially transparent that it never changes, it's immutable. So you have these very nice sort of referentially transparent pieces of data. You can run functions on those using functional language, functional operating system, and do transactional networking with Ames and Finet. And what you end up with is this world of applications where everything is stable. The names for pieces of data are stable. The names for people are stable. What a computation means is stable because it's pure functional. It's a frozen system. And so this gives a high degree of predictability, legibility, transparency, and just sort of general calmness and order to the world of building applications. And at least, I don't know about for you, but for me, for my pre-Urbit career of building applications did not feel particularly calm and ordered. So this is what we're going for. So it's local first, bottom up, and stable, right? Where the names for people are stable, the names for data are stable. If I want to do networking just you and me, we can do that. If we want to build up groups out of that, larger groups, we can do that. And so this is where the application layer comes in, where it's like, this is where you want to say, like all these post-web applications, some need to use protocols that are not inside of Urbit, but at least the clients for most of them should eventually be Urbit clients. This is our thesis. Because then they can use the Urbit identity system, they can use this operating system and all the interoperability of how these applications communicate with each other on my machine and across the network. And this is how you get to, okay, I want to start a DAO. Well, I have this DAO app on my Urbit. I can install other apps as I need to do different things with the DAO. We already have a voting app called Ballot. We have several different chat apps that are all competing with each other. And there's actually quite a large ecosystem of Urbit apps. There are over 100 of them. And there are over 4,000 people on the network on a daily basis. And it's growing. And there are over 100 monthly active developers on Urbit. So starting to pick up steam after 15 years of development. We're finally getting some momentum. Feels good. So I encourage you all to check it out. So urbit.org is where you can find out more information. There's @Urbit on Twitter. Urbit.org/start is a good place to get started. And if you want hosting, there's also Tlon.io and redhorizon.com. Red Horizon run by Brian Crane in the audience right here. And so I encourage you all to check it out. Think about how it might fit into the Web3 world that you all are building. So thank you very much.